So yeah, my name is Kading, and I'm from the University of Nottingham. And together with Claire Burridge and Jeremina, I worked on chameleon-induced quantum dynamics. And in particular, we were interested in how a chameleon field can influence the decoherence of atoms in atom interferometry. So I'm now going to tell you the following. At first, I will talk about what is a chameleon, just a short repetition. Then I will tell you what I mean by coherence and decoherence. Then I will give you a short overview over atom interferometry. And then I will show you, or explain to you how we actually performed our calculation before I then present you our final result, the master equation, and tell you what conclusions we can draw from it. Okay, so yeah, chameleon is not this animal in our case, it's actually a scalar field coming from modified gravity. And for our calculation, we used this Lagrangian here. It's the chameleon is a lambda phi 4 chameleon, and it has, of course, a metacoupling term. And due to the metacoupling, one would expect the chameleon to cause a fifth force. And one would like this force to be strong on large cosmological scales, but rather weak on smaller cosmological scales. And this can be achieved by a screening mechanism. And one screening mechanism is the chameleon mechanism, and the field which obeys this mechanism is then called a chameleon. What the chameleon does is that it adapts its effective mass to the mass density of its environment. So if the chameleon is somewhere where the mass density is very high, then the chameleon itself has a very high mass, and therefore the force is suppressed. And however, if one would create a situation in which the chameleon is not screened, then the chameleon force can actually be stronger than gravity, assumed that this coupling constant is smaller than the Planck mass. And so if there was an experiment that would have chameleons which are unscreened, then one might expect to see some physical effects. Right, and one of these physical effects could be decoherence. And if one is talking about coherence in quantum physics, then one is usually talking about coherent states. And coherent states are states which have non-vanishing off-diagonal density matrix elements. This is a very easy example. So we have a superposition of a ground state and an excited state, and the corresponding density matrix has non-vanishing off-diagonal density matrix elements. However, if you have a density matrix whose off-diagonal elements are vanishing, then you have a mixed state that corresponds to a classical statistical ensemble in some sense. And if you have a process that describes the decay of your off-diagonal elements in time, then you actually have a coherence. You have a decay of your coherence. And usually one assumes, or in general, usually coherence is assumed to be caused by environmental influences. For example, if you have a system that is coherent and you have some other system that acts on the system, then you usually expect your coherent system to experience decoherence. And one example for decoherence is actually gravitational decoherence. So you could imagine that gravity is causing decoherence in your system, and there have been some papers on this in recent years. But unfortunately, it turns out that gravitational decoherence is far too weak to be observed. It happens on very, very large time scales. However, as I said, it might be possible that the chameleon force is stronger in certain circumstances, and that's why we were thinking, maybe it actually causes decoherence which is strong enough. Okay, and if one is talking about systems that interact in some way with an environment, then one is usually talking about open quantum systems. So an open quantum system is a composite system containing a system and an environment, and both are interacting with each other. And one usually assumes that the environment is acting on the system much stronger than the system acts on the environment. This means that the environment can have a strong effect on the system, while the environment itself usually doesn't change or doesn't feel the system on large or on relevant time scales. Right, and we assume that we take an atom, consider it to be our system, and take the chameleon field to be our environment, and then see what happens. An experiment which allows to measure decoherence is atom interferometry. There one makes use of the particle wave dualism, such that one can see an atom as a wave. And one uses laser light in order to manipulate the atomic states and to create superpositions of atomic states. And one can create a superposition of two states, and each of these two states has a certain momentum. And what one wants to do is one has a source of atoms, and one wants to send a superposition of states to a target where you find a detector, and you want that your two wave function parts arrive at the same time at the same point in order to get an interference pattern. And due to the different momenta, of course, you have to force those two parts of the wave function on different paths. So what you obtain then is an interference pattern. Here you have the intensity detected in the detector, and this is the difference in the path lengths between those two paths. In the perfectly coherent case, you would get a perfect interference pattern. You would this blue line here. So you have places where you don't see any intensity at all. However, the more your system decoheres, the more this pattern converges towards a line. And there have already been experiments involving atom interferometry where people have been looking, or where people have searched for chameleons. This is one of the most recent papers about that, and they were interested in how the fifth force actually changes the length of these paths. But yeah, as I said, you can also see decoherence in that, so that's why we were interested in it. We assumed, as usually these experiments happen in vacuum chambers, so we assumed a spherical vacuum chamber, and we assumed that basically everything interesting happened in the middle, so we have some atoms sitting here. And we further assumed that the atom is so tiny and so light that it doesn't really affect the chameleon mass. And if one assumes that the chameleon looks at the chameleon profile in the middle of the chamber, then one can assume that if the chamber is the dominant contribution, that the chameleon has a constant mass, which is given by a numeric factor and the chamber radius. Okay, right. So if you have the situation that you have a system in an environment where both are scalar fields, then there's actually a very nice formula to calculate the system density matrix. It is this one here. You can find it in this nice book. And it's formulated in the closed time path formalism. So the closed time formalism is used in order to calculate an expectation value at a particular time. Instead of looking at a transition from one time to another, you just look at a particular time. And in order to achieve this, you create a closed time path. So you have an initial state at the initial time. You evolve your system along this path towards the final time, and then you go backwards. That's why we also have these labels 1 and 2 here. The most interesting object in this equation is the so-called influence action. The influence action contains information about how the environment acts on the system. It's given by this expression here. Oh, and one thing to say, of course, this scalar field here corresponds to our atom, and this curly phi here corresponds to our chameleon. And this is basically the chameleon action. Right. Okay, so what can one do with this? One can derive a master equation from it. The master equation is an evolution equation of the density matrix. It tells you how it evolves in time. So what we did was just taking the time derivative of this density matrix, and then you get this this generic expression here. And this term here is the most interesting one. We calculated the influence action perturbatively up to second order in the couplings. And then, as you can see, the master equation is still formulated in this strange basis here. There are situations where you can interpret this basis physically, but in our case, it was better to actually express our equation in terms of a momentum basis. So that's why we quantized our equation, promoted it to an operator equation, and at this point, we had to consider the path ordering of the closed time path. So an operator, or a field which has a 1 acts from the left, and a field which has a 2 has to act from the right. And then we just defined our density matrix in terms of this momentum basis, where those are the elements of the density matrix. Okay, and then what we got from this was this nice equation here. There was at least one surprising term in there. This is the final master equation. This is the standard unitary evolution term. And this is the surprising term. This is the coherence shift. It's a first order correction to this unitary evolution term. And it's basically a phase shift in the interference pattern. And those terms, they're quite similar to each other, and they're both second order terms. This is the so-called decoherence, or also noise kernel, and it describes the decoherence. And this is a diffusion, or also sometimes called dissipation kernel. It describes basically the energy exchange between system and environment. And we were particularly interested in those two terms because those are the ones which you can observe in atom interferometry. Okay, so as I said, the coherence shift causes a phase shift here in the interference pattern, and we found an explicit result for the coherence shift. Depends on the atom mass and the coupling, and also on the atom frequencies. And those two momenta here, they are actually the momenta of the two wave function parts. And as you can see, if we have a diagonal element, then the coherence shift is vanishing, and this is exactly what one would expect. The decoherence kernel was much harder to calculate. There were some subtleties here. So the standard thing to do at this point, so this is an intermediate result, on just a sketch of it, of course, would be to take the Markov limit. The Markov limit is basically the ignorance of finite time effects. And in practice, this means that one takes the upper limit of the time integration to infinity. However, it turns out that in our case, the decoherence kernel is vanishing if you take the Markov limit, unless the chameleon mass would be much larger, or larger than 2 times atom mass, which is very unrealistic. So we actually had to look at the non-Markovian case. In this case, we just consider a finite time, but there's a subtlety here. In this case, you have an initial time singularity. And this is nothing unknown. It also appears in the gravitational decoherence calculations, but in this case, they just introduced a hard cutoff, and this hard cutoff appeared in the final result, and it was not necessarily physically motivated. Also, the result was kind of arbitrary. We instead introduced a smooth coupling function, which avoids this initial time singularity, and I will explain you what we mean by that. So, without a smooth coupling function, you would have an instantaneous switch on of your interaction. But this is not realistic. What you actually have is that you have to prepare your system. So there's a preparation process, and during this preparation process, there's already some interaction between your systems. So in some sense, between your system and environment, so in some sense, you turn on this interaction not instantaneously. It has to happen smoothly. And in this way, you then avoid the singularity. And for our calculation, we show us a very simple example, but at least it allowed us to do the calculation. But at least this part here, as this happens on a certain time scale, and for everything after this time scale, the physical result should be trustworthy anyway. Right. So this allowed us then to do the time integration, and we used the stationary phase approximation to get to do the other integrals. This is again a rough sketch of our final result then, and there are 3 things to notice here. First of all, we find that t to the power of -3/2 decay. This corresponds to the decoherence. We find constant pieces, which are only dependent on this characteristic time scale, and they are artifacts of this initial smooth turn on. They are physical. They can be there in experiments, but we assume that they are small. But in principle, if they are large enough, you could observe them. And the third interesting thing is that besides the ordinary decoherence term, we also found population changing terms. So the chameleon actually populates states of the density matrix which have not been populated before eventually. But those population changes are extremely small, but they are there. Okay, this is a plot of the prefactor of our decoherence kernel. Also, this is the envelope. You see it goes to a certain value. The certain value is the shift. It's a constant shift coming from those constant terms. And here's this characteristic oscillation which one sees for non-Markovian results. We made a numerical estimate, and for this one we show a rubidium atom. Rubidium is a standard atom in cold atom interferometry. We show us a rather large vacuum chamber, but the details, this the radius is not so crucial, and we show those momenta and this coupling just to get a rough idea of what we can expect. And this should be a proportionality sign here, actually. And what you can see is that the prefect of our decoherence kernel goes with 10 to the power of minus 37. And this can be interpreted as that our decoherence time would be 10 to the power of 37 seconds, which means that the decoherence caused by chameleons is actually not observable. However, the coherence shift term is a little bit larger. It means the time on which the coherence shift is happening is smaller. It's still too small for us to observe it, but one can change some of these parameters, and if the experiments get a little bit more precise, then it might be possible to at some point observe it. But yeah, it's still tricky. Okay, so what have we seen now? We have seen that the chameleon actually causes effects on quantum particles. However, those effects are extremely small. We can't really observe it. There's a small coherence shift and there's small decoherence. However, this formalism is quite interesting because it has a lot of other applications. In principle, you can do the same calculation for a lot of other screening fields. You can look at axions, and interestingly, you could also look at dilatons. And dilatons might eventually be heavy enough to fulfill the Markov limit. Then the calculation would be even easier and potentially more precise. So there are a lot of applications which can follow from this.
Thanks a lot. Do you have questions?
So the question in general about all these experiments, suppose that reality is not a chameleon but something different, but it's not GR. Will this experiment be able to detect any deviation that is not a chameleon, you know, or is just targeted to?
So it should be able to also see other fields. As long as you have a meta coupling, as long as you have something that couples the atoms, and, it should be able to detect that. The question is whether the signal is strong enough, as we have the problem here.
Other questions?
What precise interaction is it you're testing? Just,
So
is it the same as in the previous?
We just assume we have an atom and that interacts with the chameleon. So.
And we have what? We have.
So what?
I want to know what effective Hamiltonian for the chameleon with the atom is. Which terms is it probing?
That's a good question. So we couple it to the energy momentum tensor of the atom. We assume the atom is a scalar field, so we basically just look at the only parameters which go in there are the mass of the atoms and their momenta.
Okay, so it's just the direct interaction between the masses.
More? Okay, thank you.